When you picture the heavy machinery that keeps our modern world running, your mind immediately goes to these indestructible hulks of metal.
Oh, absolutely.
Like you imagine standing next to a towering wind turbine or feeling the ground shake from a massive mining excavator, right?
Yeah, or staring up at a giant hydraulic press in a factory. The sheer scale of that equipment just screams permanence.
It really does. It feels like nothing short of a literal wrecking ball could take it down.
Yeah.
But, I mean, the reality of industrial engineering is actually incredibly delicate.
Right. It's much more fragile than people think.
Because we forget that these giant machines, well, they actually have lungs.
I love that analogy. It is a phenomenal way to think about it because they really do breathe. I mean, as a machine operates, the internal fluids are constantly pumping out to, say, hydraulic arms or cycling through these massive gearboxes.
And when fluid leaves a reservoir, air has to rush in to fill that empty space.
Exactly. Otherwise, you create a vacuum. Add in the fact that these machines heat up and cool down constantly, which causes the air inside to expand and contract.
Oh, sure. So the machine is literally inhaling and exhaling the atmosphere around it all day long.
Yeah, it's a system that is constantly breathing.
And that inhalation is exactly where the danger lies, right? Because the greatest threats to these massive systems aren't the things you can see. It's not giant rocks or structural stress.
No, the real enemies are invisible.
Right. It is microscopic dirt and plain old moisture in the air. So our mission for today's deep dive is to understand the ultimate high-tech respirator for those industrial lungs.
It's a fascinating topic.
We are looking into the engineering behind the TDB Series breathers by RMF Systems, which is a DES-CASE brand.
Right.
We really want to understand how a relatively small, unsung hero of the industrial world keeps our vital infrastructure from, well, basically suffocating on its own environment.
Because in the world of industrial maintenance, preventing contamination from entering a fluid system in the first place is always, and I mean without exception, cheaper and safer than fixing a catastrophic failure after the fact.
Yeah, you don't want to be replacing a massive turbine gearbox if you don't have to.
Exactly. And what makes the TDB series so compelling isn't just that it acts as a simple filter.
Right, it's much more than that.
Yeah, it's the highly specific way it chemically manages moisture, how it survives these intense corrosive environments, and how it fundamentally shifts how ongoing maintenance is handled in some of the most unforgiving places on the planet.
Okay, let's unpack this. Because before we get into how much punishment these breathers can take out in the field, we first need to understand how they are actually built.
Right, the anatomy of the breather.
Yeah, how they physically separate clean air from the toxic elements of an industrial site. At the very core of this unit is a structural standpipe, and it's made of heavily reinforced glass-filled nylon.
Which is an incredibly tough material.
Right, glass-filled nylon is super rigid, which makes perfect sense for something vibrating on a giant machine all day. But what really caught my eye in the specs is that this standpipe features a built-in oil mist reducer.
Oh, yeah. That's a critical design feature.
So the way I'm picturing this, the built-in oil mist reducer is basically acting like a bouncer at a club.
A bouncer. I like that.
Yeah. Is making sure the churning oil inside the machine doesn't splash up and ruin the protective gel before the gel can even do its job of catching the moisture from the outside.
That is a highly accurate way to visualize it. You have to remember that the environment inside a high-speed gearbox or a hydraulic reservoir isn't a calm pool of liquid.
No, it's probably chaotic.
It is incredibly violent. Oil is churning, splashing, and constantly atomizing into this fine mist.
Right.
If that oil mist were allowed to travel freely up the neck of the breather, it would coat the active desiccant gel sitting right above it.
And that gel is what traps the water, right?
Exactly. And desiccant relies entirely on microscopic surface area to capture that water. So if those pores get coated in a layer of oil, the gel becomes completely blind and essentially useless.
Wow, so the machine would just be sucking in wet air anyway.
Yep. So that reinforced standpipe physically shields the active ingredients of the breather from the machine's own internal chaos.
And the active ingredients themselves are, well, they're just fascinating. The defense starts with the particulate filter, which has an efficiency rated at 3 micrometers or microns absolute.
That's a very important specification.
And for anyone listening who isn't spending their weekends reading fluid dynamics textbooks, 3 microns is absurdly small.
It really is.
Like, to put that in perspective for you, a single human hair is roughly 70 microns across.
Right.
A white blood cell is about 25 microns. So we are talking about stopping particles that are essentially the size of smoke.
Yeah, it's virtually invisible to the naked eye.
And the documentation specifically uses the term absolute, not nominal, with a beta ratio greater than or equal to 200. Can you break down why that specific distinction is so critical?
I can, absolutely. When you buy a cheap furnace filter for your house at the hardware store, it usually has a nominal rating.
Okay.
That means it catches most of the particles of a certain size, maybe 50 or 60% of them.
Like it catches the big stuff, but lets some slip through.
Right. But an absolute rating with a beta ratio of 200 is in a completely different league mathematically.
How so?
A beta ratio of 200 means that for every 200 particles of that 3-micron size that try to pass through the filter, only one single particle actually makes it through.
Wow. Okay, so that is a 99.5% capture rate?
Exactly. It's a 99.5% capture rate for particles the size of a smoke ring.
Which seems almost like overkill, honestly, until you realize what a 3-micron piece of dirt can do inside a machine.
Precisely. Because inside a high-pressure hydraulic pump, the microscopic clearances between the moving metal parts are often only 2 to 5 microns wide.
Oh, wow. So they are tighter than the dirt itself.
Right. If a 3-micron particle slips past the breather, it fits perfectly into that gap.
That sounds like a disaster.
It is. It acts like a microscopic wedge of abrasive paste. It scores the metal, gouges out more metal particles, and starts this explosive chain reaction of wear that destroys the pump from the inside out.
Just from one piece of dirt.
Yeah.
That's wild. So the TDB series uses a specialized glass fiber filter media to achieve that absolute rating. But, dirt is only half the battle here.
True.
The other half, and often the much more insidious half, is water.
Water is the silent killer in hydraulics.
Right. Which brings us to the ZR gel. This is the material that handles the moisture. It's described in the specs as a hydrophilic media made up of these little 3 to 6 millimeter beads.
Hydrophilic, meaning water-loving.
Exactly. So they aren't just acting like a physical sponge soaking up a spill. They are chemically attracting the water vapor from the incoming air.
Yeah, they actively pull the humidity right out of the atmosphere.
Right, and they lock it deep inside their microscopic pores so it can't pass into the machine. But the cool part is they don't just sit there in the dark doing this. They actually communicate with you.
That's one of my favorite features.
The breather has this passive visual indicator, right? So the ZR gel changes color from red to a bright yellow to indicate when it is fully saturated with water.
What's fascinating here is how this passive design actually changes human behavior on a massive industrial scale.
How do you mean?
Think about a typical industrial plant. It's noisy, it's messy, it's high stress. If you rely on complex electronic moisture sensors, they can fail.
Oh yeah, wiring gets corroded all the time.
Right. Or the warning light on a dashboard somewhere gets ignored by an overworked operator. But having a clear, passive visual cue right on the machine where red means it's active and protecting, and yellow means it's full of water and needs attention, it completely removes the guesswork for maintenance crews.
It makes it idiot-proof, basically.
Basically, yeah. It fundamentally changes how proactively a facility can operate. A technician can be walking down a catwalk 30 feet away, look down at a piece of equipment, and instantly know the status of its lungs without ever plugging in a diagnostic computer.
It's just brilliantly simple. And the materials holding all of this together, they have to survive the very environments they're protecting the machine from.
Absolutely. They have to be tough.
So you've got a copolyester body for the main housing, which provides massive impact resistance. You have Bunyan seals, galvanized steel components, and these silicone check valves.
Yes, the check valves.
But let's pause here and really look at those check valves, because this is where the engineering really threw me a massive curveball.
Oh, really? How so?
Well, we know the anatomy of the breather now, right? We've built this impenetrable fortress against dirt and water.
Right?
But a great filter is completely useless if it suffocates the machine. The machine still has to inhale.
That's true.
I'm looking at the operating limits on the spec sheet. It survives temperatures from negative 40 degrees Fahrenheit.
Which is where most plastics become incredibly brittle and shatter, by the way.
Right.
Yeah.
All the way up to 194 degrees Fahrenheit, which is nearly boiling.
Yep.
And the Bunyan seals ensure it's chemically compatible with harsh synthetic oils, mineral oils, diesel fuels. It is clearly built for an absolute war zone. But then we hit the airflow dilemma.
Yes, the great airflow trade-off. I wondered if you'd catch that.
I have to push back on this design choice, I really do.
Okay.
Because if you look at the flow dynamics, an open breather without check valves allows a massive amount of air to flow freely.
It does.
We're talking up to 53 cubic feet of air per minute on the larger models.
Right.
But if you configure the breather with check valves, that maximum airflow just drops off a cliff. It plummets down to just 14 cubic feet per minute on that exact same large model.
It's a significant drop.
Wait, if adding check valves cuts your maximum airflow by more than half, why on earth would anyone choose to use them? Are you just choking the machine and risking a vacuum in your hydraulic reservoir?
It seems entirely counterintuitive at first glance, I agree. Why would you purposefully restrict the breadth of your own equipment?
Exactly.
But this is where the brilliance of pressure physics comes into play. You aren't choking the machine, you are creating an intentionally closed system.
Okay.
Those silicone check valves have a highly specific cracking pressure of 0.05 psi.
0.05 CSI. Just to visualize that for everyone, 0.05 CI is an incredibly light amount of pressure.
It really is.
It's practically the weight of a gentle human breath.
Exactly. It's an incredibly delicate threshold, but it's just enough pressure to ensure the valves remain totally shut under normal, idle conditions.
So they just sit closed when the machine isn't doing anything.
Right. Think about what happens without check valves. An open breather is constantly exposed to the ambient environment.
Oh, I see where you're going with this.
Yeah, even if the machine is turned off for the weekend and therefore isn't actively inhaling or exhaling fluid, the ambient humidity in the air can still slowly diffuse into the desiccant gel, exhausting it prematurely.
Like leaving a bag of chips open on the counter. The humidity ruins it even if you aren't eating them.
That's a perfect analogy, yes.
I see. So the check valves act like a permanent seal when the machine is resting.
Precisely. By installing check valves with that exact 0.05 psi cracking pressure, the breather only opens when the machine absolutely forces it to.
So only when the fluid moves.
Right. During a fluid volume change or when the machine heats up and the internal air expands, the pressure inside the reservoir hits that 0.05 psi threshold.
And then it pops open.
The valve pops open, releases the breath, and then instantly snaps shut again, resealing the vault.
Wow.
This drastically extends the life of the ZR gel, particularly in highly humid environments like coastal shipping facilities or sweltering paper mills.
So you are making a deliberate trade. You are sacrificing maximum theoretical airflow in exchange for drastically increased longevity and total atmospheric isolation.
That's exactly it.
But that means you really have to do your math before bolting one of these onto a machine. You can't just guess.
You absolutely cannot just guess. Sizing a breather isn't just a matter of looking at a pipe diameter and screwing it on.
Right.
You have to calculate the ambient humidity levels, the extreme temperature swings, and most importantly, the frequency and speed of the airflow.
Give me an example of that.
Sure. If you have a massive hydraulic press that displaces hundreds of gallons of fluid in a fraction of a second, it needs a massive amount of airflow instantly to prevent a vacuum from forming and imploding the reservoir.
Oh, right. So in that case, you need the open version without the check valves.
Exactly. But for a massive gearbox that only breathes slowly as it warms up in the morning and cools down at night, the check valve version is vastly superior because it preserves the gel for months or even years longer.
Which perfectly transitions us into how RMF systems actually scales this defense across different industries. Because, industrial environments and airflow needs vary so wildly, a one-size-fits-all approach would just be a complete disaster.
It would never work.
Right. You can't put a tiny breather on a massive turbine, and you don't need a massive breather on a small pump. When you look at how they scale these units, the difference in capacity is staggering.
They are engineered to address vastly different volumes of air and atmospheric moisture.
Let's break down the physical reality of these units. The spec sheet lists 3 main sizes, right? The 93, the 96, and the 121.
Yes, those are the primary models.
So you have a compact size, the 93, that sits about 6 inches tall and holds just over half a pound or 320 cc of the ZR gel.
Right.
And that little unit can chemically capture about 3 fluid ounces of water.
Which is pretty impressive for its size.
It is. Then you step up to the 96, which holds about a pound of gel and catches 5.5 ounces. But then you scale all the way up to their massive model, the 121.
The big one.
Yeah, which is nearly 10 inches tall, holds almost 2 pounds of desiccant over 1,000 cc's, and can trap an impressive 10 fluid ounces of water directly out of the air.
10 fluid ounces of water might just sound like a normal glass of drinking water, but remember the context here.
Right, it's not a puddle on the floor.
No, we are talking about water in the form of invisible ambient humidity. To pull 10 ounces of liquid water completely out of thin air requires chemically processing an enormous volume of atmosphere.
That's a huge amount of air.
And you have to consider what would happen if those 10 ounces actually made it into a high-pressure lubricating system.
It'd be bad news, I assume.
Water in oil causes hydrogen embrittlement in bearings, it accelerates rust, it forms corrosive acids, and it utterly destroys the lubricating film thickness. Yeah. 10 ounces of water could easily cause tens of thousands of dollars in catastrophic damage to a gear set.
And it isn't just the sheer size of the units that scales. It is how they physically interface with the machinery.
The connections. Yeah.
They offer all the standard industrial connection types. You have standard pipe threads like NPT for North America, BSPP threads for Europe, and standard flange bolt patterns like the Denon 6-hole pattern.
That's a huge advantage for global operations.
Here's where it gets really interesting, though. Look at the massive variety of industries that utilize these exact same connections.
It covers almost everything.
It really does. You have wind energy sitting hundreds of feet in the air. You have pulp and paper mills, which are essentially giant, humid steam rooms.
Very harsh environments.
You have open-pit mining operations choked with abrasive dust. You have petrochemical plants, aviation, mobile off-road equipment, and even nautical applications out on the open ocean.
Yep.
You're telling me the exact same core technology protecting a stationary sweltering paper mill is also bouncing around on a heavy-duty truck differential or getting blasted by salt spray out at sea. That's wild.
It is wild, but if we connect this to the bigger picture, it highlights a fundamental universal truth of the industrial world.
Which is?
Fluid dynamics and the physics of contamination do not care about your zip code.
Oh, that's a good way to put it.
It really doesn't matter if your gearbox is on a mining excavator deep underground in high dust conditions, or if it is inside a wind turbine nacelle dealing with massive temperature swings.
The oil still degrades the same way.
Exactly. The physics of how oil degrades, how air carries moisture, and how water destroys metal remain exactly the same across the board.
So the protection has to be the same.
Right. And the genius of offering those standard pipe threads and flanges is that it allows this highly specialized niche technology to seamlessly interface with almost any piece of legacy machinery in the world.
Oh, right, because you don't have to rebuild the machine.
Yeah, exactly. A plant manager doesn't have to redesign a 20-year-old pumping station to fit a modern defense system. The breather is engineered to adapt to the pump.
That adaptability is obviously crucial for adoption. But it also introduces a massive logistical problem. And this brings us to the design's endgame, really.
The maintenance side of things.
Yeah. Let's say you have these breathers deployed across a massive industrial footprint. Imagine thousands of them across a single mining operation, or bolted onto every single wind turbine in a massive offshore wind farm.
That's a lot of breathers.
It's a ton. If you had to unbolt and throw away the entire physical unit every time the gel turned yellow, you would create an enormous amount of physical and financial waste.
Oh, absolutely.
You'd be tossing perfectly good galvanized steel, heavy-duty copolyester housings, and glass-filled nylon standpipes into a landfill just because the consumable gel inside had reached its capacity.
Which, ironically, is exactly how the industry used to operate.
Wait, really? They just threw the whole thing away?
Yep. For a long time, disposable breathers were the standard. Once they turned color, you threw the whole chunk of plastic away and bought a new one.
That is so wasteful.
It was. But that is exactly why this specific engineering document highlights, right at the top, that the TDB series is fully serviceable. They are moving entirely away from the disposable mindset.
So what does this all mean for the people actually running these plants?
It means a complete shift in maintenance strategy.
Because I see in the documentation they have these spare parts like the KL90 and KL120 air filters and these RF series gel refills.
Right.
They've actually designed comprehensive spare kits, the RK93, the RK96, the RK121. And these kits contain exactly what gets consumed. A fresh air filter, new batch of the ZR gel, new foam filters, and a replacement bottom seal sticker to make sure everything stays airtight.
Yeah, they give you exactly what you need and nothing you don't.
So you aren't tossing out the durable body or the check valves, you just swap out the lungs.
Exactly.
You dump the saturated gel, pop in the new dirt filter, reseal it with the sticker, and the heavy-duty infrastructure of the breather remains right where it is, practically brand new.
This modular approach to maintenance is really a masterclass in modern industrial design.
It really is.
By intentionally breaking the system down into consumable parts, meaning the gel and the filters versus permanent infrastructure, like the housing and the check valves, companies can maintain that optimal 3-micron moisture-free protection with a fraction of the downtime.
Because you aren't unscrewing massive pipe fittings.
Exactly. A technician can walk down a line of hydraulic reservoirs, spot the yellow breathers, and literally rebuild them right there on the catwalk in minutes.
That's so efficient.
It dramatically lowers the total cost of ownership over the lifespan of the machine. But perhaps more importantly, it significantly reduces the environmental footprint of the maintenance program itself.
Because you're only trashing the biodegradable parts.
Right. You are throwing away a filter and inert gel rather than pounds of heavy industrial plastics and metals every few months.
It makes so much sense. I mean, it's the exact same logic as changing the oil filter in your car instead of throwing away the whole engine block when the oil gets dirty.
That's a great comparison.
Except here, we are doing it on a multi-million-dollar scale to protect the heavy infrastructure that literally keeps the modern world turning.
It is a massive scale.
It really changes your perspective on how these massive facilities operate. I mean, you start this journey looking at the giant, highly visible threats to machinery, right?
The heavy loads, the extreme heat.
The massive physical forces, exactly. But then you realize the real war is actually being fought at the microscopic level.
The invisible war.
We've gone from understanding the hidden catastrophic threat of a 3-micron piece of dirt and invisible airborne water to unpacking the incredibly specific engineering required to stop it.
It's quite a journey.
We've seen the chemistry of hydrophilic gel that visually communicates with the technicians, the delicate physics of a .05 side check valve that dictates exactly when a machine can inhale, the industry-wide adaptability from mining to aviation, and finally, this brilliantly sustainable modular design that prevents massive waste.
This raises an important question for you to consider long after we wrap up today's conversation.
Oh, lay it on us.
We constantly look at the massive moving parts of our modern world, the spinning wind turbines against the skyline, the towering excavators moving literal mountains of earth, the giant cargo ships crossing oceans.
Right, the stuff that looks impressive.
And we view them as the absolute pinnacle of human engineering. But how much of our global progress is actually dependent not on the giant machines themselves, but on our ability to engineer microscopic, invisible defenses at the exact point where those machines meet the open air?
It's a humbling thought, isn't it? The biggest, toughest machines on Earth rely completely on the smallest, most delicate filters to survive.
They really do.
Thank you for joining us on this deep dive into the invisible world of industrial breathers and the hidden mechanics of keeping heavy machinery alive. Keep questioning how the world around you actually works, especially the parts that are too small to see.